Hello guys, this is Linksels here, and today we'll be continuing boron. Now that's out of the way, let's get into it. Boron is one of 16 essential plant nutrients vital to the plant's life cycle, required only in small amounts. Boron is necessary in plants to control flowering, pollen production, germination, and seed and fruit. It also helps to convey from older leaves into new growth areas and root systems. Important industrial uses of boron and trace amounts include controlling the electrical behavior of some types of superconductors and increase the hardness of steel. A brilliant green color used in pyrotechnic flares to signal or illuminates, and in fireworks. Chapter 5: Boron compounds and alloys. Boron compound combines with other elements to form compounds and alloys. Can you hear me? Oh, wait, you can't. Sorry. Compounds always form in fixed portions. So that boron oxide B2O3 always pairs two boron atoms with free oxygen atoms. Alloys are a mixture of mostly metals that often use non-metals like boron. The substitute for a small portion of other elements in the alloy. The substitution into the particles of the nutrient such as color and strength. The compounds that boron forms are held together by covalent bonds. In covalent bonding, valence electrons are shared between atoms. The attraction of each atom on the shared electrons is what is paired from one another in an atom in the compound. However, in boron, the compound in which from hydrogen, valence electron pairs are spread across free atoms. The structure of these interesting and unusual compounds called boron hydrates or borides, borons remain unknown until about 1950. Borides, which include familiar boron compounds such as borax and boric acid, are formed with oxygen, and this family of compounds accounts for most of all the industrial uses of boron. Many boron compounds are also formed with halogens, elements from group VIIa, or 17, metals and organic carbon-containing components. Borides, boron-oxygen compounds. The most common boride is borax, which is also why it's called sodium turbidate, Na2B4O7. Sodium boride is usually hydrated or attached to water molecules. Borax is sold in groceries as a laundry booster. It's called borax dehydrates, Na2B4O508.8H2O. Forming the equivalent of 10 water molecules. Ding. Beep. Other useful formulations that have the equivalent of 5 water molecules: pentahydrate, and no water molecules, antihydrate or anhydrous. Boric acid, another common borate, occurs naturally in some hot springs and volcanic areas, but is usually commercially derived from borax compounds. Borides are used in laundry and dishwashing detergents, eye wash, and contact lens solution. However, the biggest borate market is fiberglass. Insulation fiberglass provides thermal and acoustic insulation for homes, buildings, and vehicles. Textile fiberglass is used for fabrication of items such as surfboards, circuit boards, and dashboards. Borates are also a key ingredient in the heat-resistant glassware, familiar under Pyrex brand name, and found in the laboratory and kitchen. Wait, hold on. If it's heat-resistant, resist not proof. I was going to say, if it's heat-proof, then how are you going to shape it? Hmm? Brand name and found in the laboratory or in the kitchen. These uses together with enamels and glazes accounted for 70% of the U.S. boron consumption in 2004. Other boron uses are diverse and can be found in agriculture, wood treatment, poultry, automobile manufacturing, and pyrotechnics. To name a few fields, agricultural uses include fertilizer that satisfy the plant's natural need for boron and pest control that explodes boron's toxicity. In high doses to insects and plants, this toxicity is also used as a wood treatment to protect against fungus, bacteria, and insects. Some borates dissolve and scavenge metal oxides. These properties are used to refine metals by taking away impurities. Borates can also inhibit corrosion and clean surface metals to be welded or brazed. Other borates serve as fuels and colorings and pyrotechnics, and as explosives to ignite compounds that fill vehicle airbags when they burn. Wait, and as explosives to ignite. Doesn't make any sense. And as explosives to ignite compounds that fill vehicle airbags when they burn. Now, if that makes any sense to you, please put it into the discussion below. Wait, there's no discussion below. The comment section below. Please, put it into the comment section below. Crystallized boric acid is a waxy platinum structure that gives it a slippery feeling, making it a useful component in lubricants, cosmetics, cold cream, and pencil leads. Boric can tie together along. Oh wait, no. Hold on. It's not the comment section below. It's actually the discussion. Just hit the discussion section and then you see the discussion. Did anyone understand that? Really? No? No one? Oh, fine. Crystallized boric acid is a waxy platinum structure that gives it a slippery feeling, making it useful components in lubricants, cosmetics, cold cream, and pencil leads. Borates can tie together long-stranded molecules with protein units called polymers, an action known as cross-linking. Borate cross-linkers are used to strengthen cement, enhance adhesives, and help recover oil and gas. They're also the basis for such popular toys such as slime and silly putty. Boranes. Oh, boranes. Boron, hydrogen compounds. Dorbane. Oops. Debornane. B2H6, a colorless gas at room temperature, has a wide range of applications. It is used in the production of integrated circuits where the small amounts of boron atoms diffuse into silicon modify the electrical conductivity. The borane also speeds up the production rates of some polymers, molecules, crosslinks, natural rubber to make it more useful, and it is used in the production of hard boron coatings on metals and ceramics. It was once investigated for use as rocket and jet fuels. Boranes never reached potential, but possible despite intense research around the 1950s and early 1960s. More generally, boranes can cover organic carbon-based molecules that are unsaturated into other molecules, able to react with additional hydrogen into other molecules. Cross-linking use in oil and gas recovery. In oil and gas recovery, the rock reservoir holding the material is fractured by pumping high-pressure fluids down wells. The fractures give the oil or gas a path to the well, where it can be brought to the surface. Cross-linked gels are thick and gluey and help carry granular material down the well and into the fractures to be propped open. And was continuing into other kinds of organic molecules. Dang. Step 1 is to pour some borax. Step 2 is to melt that borax. And then add some glue. Step 3, pick it up with something. Step 4, let it sit. Step 5, pull it apart. Step 6, enjoy. And then you got your thing. The process called hydroboronation. This discovery resulted in the 1979 Nobel Prize and has been led to inexpensive method of organic compound production. Anyways, tomatoes are gross. One of these methods facilitates the formation of an organic compound of a specific shape while producing none in the form of its mirror image shape. The two shapes are called optical atomisers. This ability to make only one is more form is important because living things usually produce and use only one shape and not the other. Before the boron-based method was discovered, the manufacture of medicines with just one desired isomer would usually produce both, which were expensive and difficult to separate. Other boron compounds. Boron combines with nitrogen to form boron nitrate, Bn, which has 3 different forms. Cubic Bn has the same crystal structure as a diamond, and is almost as hard. It is used as an industrial abrasive for grinding and cutting metal. Hexagonal Bn has a sheet structure like graphite. Like the tip of your pencil. Graphite. Graphite. And is used for lubricants and cosmetics. Unlike graphite, it is stable at higher temperatures. The first form of Bn is bound to bowl-like molecules. These are being studied for use in delivering medical compounds to cancer cells in the body. And used as a fuel, those bonds store substantial energy. The ceramic material, boron carbonate, B4C, is another extremely hard material, ranking third just below boron nitrate and diamond. Boron carbonate is used in tank armor, bulletproof vests, and as an abrasive. It's also embedded in aluminum to make a strong, lightweight material used in bicycle frames, for example. Boron forms other hard ceramic materials with metals in a class of compounds called borides. Borides tend to have high melting temperatures. Metals that form borides include aluminum, calcium, cerium, chromium, hafnium, iron, magnesium, niobium, titanium, and titanium. Also, I recommend you do not skip from this part or before this part. Oh, wait. It's too late now. Anyways, go skip back if you already skipped to this part. Now, because it's something interesting. I need. Please, let's listen. Tungsten, vanadium, and zirconium magnesium boride displays nearly zero resistance to electrical flow at about 36 degrees Fahrenheit, 2.2 degrees Celsius above absolute zero, or negative 459.7 -76 degrees Fahrenheit, negative 273.15 degrees Celsius. Compounds that display this behavior are called superconductors. Boron compounds with halogens, especially boron fluoride, are widely used as catalysts, which accelerate chemical reactions. Halogens are the group VIIA or 17. Elements, fluorine, chlorine, bromine. Oh, by the way, if you don't know what bromine is, go check out Blaze Alien. He has that video. Yeah, go check it out. Anyways, iodine and acetine. By the way, I'm not going to do acetine since it's not there, so bye. You really thought that was the end of the video, right? It can usually be like 20 minutes. Yeah, you're going to be 20 minutes. Haha. Boron bromide. What? Is used in manufacturing fiber optic cables. Boron alloys. Boron hardens some alloys, enhances magnetic properties in others, and is used to protect metal surfaces from corrosion. And still others. In small amounts, boron hardens steel, making it more resistant to ductile failure. Failure. The boron is usually provided in the form of an iron and boron alloy, which is also used in manufacturing the cores of electric power distribution transformers. And some alloys fuse as protective coatings to metal surfaces. Boron is included as an alloy component to clean these surfaces. Chapter 6. Oh, I know. Plates made from boron carbonate, a very hard lightweight ceramic, are used in bulletproof vests and body armor, as well as tank armor and abrasives. Chapter 6. Boron and new. Boron compounds have been known for at least 1,000 years as ores, and from hot spring waters, although traditionally used in laundry-boosting compounds. Boron shows up in some surprising places, like pie pans, and MP3 players, and futuristic electricity sources. Borosilicate glass. If you have seen a pie baked in a glass pan, chances are the pan was made from heat-tolerant borosilicate glass. The main ingredients of this glass are boric acid, silica, soda, and lime. The glass has come to known as Pyrex, a brand of borosilicate cookware that was introduced in 1915 by the Corning Glass Works Company, CGWC. CGWC. Typical soda lime glass, which lacks boron, breaks more easily from the thermal stress that are created when going between room temperatures and cooking or baking temperatures. However, the addition of boron reduces thermal stress. Oh my god. Dresses. Yes, I had used my assistant. The truth is, I don't have an assistant. Anyways, back to the book. By reducing the thermal expansion of the glass, it also raises the temperature where the glass softens from 1,350 degrees Fahrenheit, 730 degrees Celsius, to about 1,500 degrees Fahrenheit, 820 degrees Celsius, and reduces electrical conductivity. Besides bakeware, other early uses of borosilicate glass included laboratory glassware, railroad lantern lenses, and insulators used to suspend high-power electrical lines from poles. And that was today's video. I hope you guys enjoyed it, and I'll see you guys again very, very soon. Bye.